How can you do?
Is that a Bugatti? It's crazy.
It was parked outside my house.
Why a Bugatti gauge rod?
And you didn't take it?
I know a guy.
Oh, Jacob. I applaud you, Jacob. Good job, sir.
All right, so we're going to talk about parametric surfaces. So we've worked with parametric equations of curves in the plane and in space. And we looked at them as parametric equations and as vector-valued functions. So we're going to do something similar with surfaces. So for curves, though, we use a single parameter, usually t or maybe theta. For surfaces, our parametric functions, our parametric equations are going to be functions of two variables. So I just want to run down just the different types of representations we've talked about so far. So for curves, we have the explicit form. This is the one we're most familiar with. Explicit form, we have y equals f of x. We also have implicit form, and we've worked a little bit with, you've worked with those in several different contexts. We have f of x comma y equals a constant. In Calc 1, you use these kinds of functions when you talked about implicit differentiation. We talked about the gradient being normal to level curves. So this would be a level curve of a surface. And then we also talked about parametric, which or vector, because we use the parametric equations as components of our vectors. So our parametric or vector form would be r of t equals f of t I hat plus g of t j hat on some interval for t. We have something similar for surfaces. We have explicit form. So our explicit form for a surface is z equals some function of x, y. And we've worked with the implicit form. The implicit form turned out to be very important when we were talking about normal vectors, the gradient as a normal vector. We had f of x, y, z equals a constant. And our gradient was a normal vector to a surface f of x, y, z equals a constant. Today, we're going to talk about parametric form. Our parametric form, we're going to have r of u and v. And we're going to have some f of u and v I hat plus g of u and v j hat plus h of u and v k hat. And f, g, and h are some nice functions in what we call the UV plane. Now, a couple of examples that we didn't necessarily think of as being parametric surfaces or writing our surface in parametric form is when we talked about cylindrical coordinates or spherical coordinates. X is some function of r and theta, y is some function of r and theta, and z is some function of r and theta. Z is just z in cylindrical coordinates. And in spherical coordinates, f is some function of rho and phi, y is some function of rho and phi, and z is some function of rho and phi. Actually, rho, phi, and theta. So we're going to say that r of u and v, this is our parametric surface. and F, G, and H are the parametric equations. For the surface. So we can think of this just like we did with parametric equations for a curve and vector valued functions for a curve. The parametric equations are the components of our vector valued function. A couple of things. Vector valued functions are not unique, just like parametric vector valued surfaces are not unique, just like parametric equations are not unique. If we parameterize the surface in a different way, we get a different different representation of the same parametric surface. And what we're mostly interested in today is how we're going to visualize parametric surfaces. So to visualize them, to sketch them, we do something similar to what we did with parametric equations, where we want to look for a relationship between the components, the x, the y, the z, or eliminate a parameter somehow to come up with a familiar equation. Finding a parametric equation for some particular surface, it can be very difficult unless the surface is a nice, easy surface. So a couple of exceptions are when we talk about cylindrical and spherical coordinates. We have an idea of how to do that for nice surfaces. And if you want to look, the cover of our book is actually a very, very complicated parametric surface, and they give the parametric equations along the spine there. It's pretty complicated parameterization. It's kind of a Mobius surface, yes. It's like a Mobius bagel. And then on the pre-calc book that we used, that's a parametric surface as well, but they don't give the parametric equations for the surface on the cover of the book. All right, if we have an explicit representation of our surface, if z equals f of xy, so we know the explicit representation, we can say our parametric surface r of x and y is just x I hat plus y j hat plus f of xy k hat. And that would be a parametric representation of the same surface. We just parameterize it in terms of x and y. Just like we can parameterize a familiar curve in the plane, letting x be the parameter. All right, so the first thing that I want to do is look at some graphs and match the graphs to their parametric representations. So let me grab that picture. Let me zoom in, make it a little bigger. 150. That's going to be good. There's that. All right, so we want to match the surface to the graph, and this will give us a little, we'll be able to look at how we visualize these a little bit. All right, so we're going to, let's look at number one. So for number one, what we want to do is look for a relationship. This is u I hat plus v j hat plus u v k hat. So we want to look for a relationship. Maybe I'll make it this, let me erase this and I'll make it a little bigger so we can see the equations a little better. If I make it too big, they get a little blurry. There we go. A little better. All right, so what kind of relationship do we see between the variables here? Z equals x times y, right? This is z, this is x, this is y. Z equals x times y. So what kind of surface is that?
Hyperbolic parabola.
It's B. Either A or B.
No, it's definitely B.
It's
Epsilon.
E?
Correct.
Oh, so it has to be
Why
zero.
red is B?
It has to be zero anywhere either of the two variables are zero.
That's
Well,
zero
so-
on the x-axis.
So
zero
let's
on the
let's
y-axis.
let y be a constant. Or let me do it a different way. We have y equals z over x. If y is a constant, what kind of graph is z over x equals a constant? Z equals 2y. Z equals 3y. Z equals 4y. So what would that be? Or z equals 3. Z equals 4. Z equals 5. Well, let's leave that one for now and look at some other ones. Maybe we can eliminate a few and look at some other ones. Number two, we have r of u and v equals u cosine v, u sine v, and z equals u.
C. Actually, the sine, cosine, and then a z. It's just z. That's just circle.
So these, when we see sines and cosines, we should think are Pythagorean identities. So x squared plus y squared equals u squared times, I'm going to factor, so I'm going to square this and square that, cosine squared v plus sine squared v. And this is 1. So x squared plus y squared equals u squared, which is z squared. U squared is z squared?
D.
What is that?
Wow.
No, it's not D.
That's
It's a cone. Double mapped.
Z, for a constant value of x, z squared equals y squared, z equals y plus or minus y.
How'd you get x squared plus y squared z squared?
X squared plus cosine squared v plus sine squared v is 1. So x squared plus y squared is u squared, and z is u. Z equals u. It's a cone. So that's F. Number 3. We have u I hat plus 1/2 u plus v j hat plus v k hat. So this, if we look at the relationship between the components, 1/2 u plus v x plus z equals y. That is a plane. So that would be B.
So then 1 would be
1 is E.
We're thinking 1 is E? Yeah, hyperbolic.
Yeah, because then it's like it's 0 on all of the axes, which is what
Right,
is-
0 on all the axes, yeah. Okay. Let's do a couple more to make sure that we're good with that assessment. Number 4, we have u I hat plus 1/4 v cubed j hat plus v k hat. So the relationship I see here is between y and z. So z equals, or so I'll do it the other way around. Y equals 1/4 z cubed. So we have the cubic relationship between y and z. So that has to be a.
Cubic.
Number 5.
I don't
2 cosine v cosine u I hat, 2 cosine v sine u j hat, 2 sine v k hat. Anybody recognize what kind of coordinates? Those are spherical coordinates, right? But we're using u and v instead of phi and theta. So let's look at our relationship. Whoops, I didn't mean to circle number 5. I'll put number 5 over here. Let's look at our relationship there for number 5. X squared plus y squared. I'm going to square both of these. We get a 4 cosine squared v. And I'm going to factor that out of a cosine squared u plus sine squared u. So that just gives us 4 cosine squared v. Well, how are we going to relate that to the z component?
You add 1 minus.
All right, x squared plus y squared plus z squared equals 4 cosine squared v plus 4 sine squared v equals 4. That's a sphere. So that is, which one's a sphere? D. And this is just a parametric representation of spherical coordinates. All right, let's look at number 6 finally. The only relationship here is between x and y. X squared plus y squared equals 4. 4 or 16. And z just equals z. Z is anything. X squared plus y squared equals 16. What is that? Circle in 3 dimensions. Cylinder. So that's got to be C. And A, or number 1, has to be this hyperbolic shape here. And when I see this, I think, okay, that's a hyperbola. We're going to have a hyperbolic shape. So that has to be E. I think the one that had the easiest relationship between the variables was the most difficult to visualize.
It's not what you expect. So that's
Right.
what I'm thinking about.
Right. All right, questions there? So this is like parametric equations, but not just plus 1, but kind of times 2. It gets not just one more difficult, it gets a multiple more difficult. All right, let's look at going the other direction. From parametric form to rectangular form. So we want to find the rectangular equations for these. So this would be an example of the type of question that might be on the quiz on Thursday. This type of idea.
What was that? Yes. It's not yes, but I can't say it is.
Well, this type of problem, or these types of problems that we're talking about here.
It's going to be appearing on quiz day. That means
Not this problem. This type of problem.
integral of the day. I think you guys are looking too deep into this.
I think you're looking.
All right. So what relationship do we see here? What components can we relate? Y and Z. So Z equals y over 2. And x is just whatever. What is this thing? I could write this as y equals 2z or y minus 2z equals 0. What is that? That's a plane.
You just ignored the X.
The x can be anything, yes. So what does that tell us about the plane?
It's infinite z direction.
It's parallel to the x-axis. Right. Yeah.
So that's all you have to do is like, once you put to z equals y over 2, that'd be fine?
Yeah.
Okay.
If you wanted to identify what kind of surface it was, you might use something else. But once you see a linear relationship, you know it has to be a plane. So there's number 1. Number 2, R of u and v equals 2u cosine v I hat plus 2u sine v j hat plus 1/2 u squared k hat. Yeah, let's look at the x and y component together. So x squared plus y squared. What are we going to get when we do x squared plus y squared? 4u squared, which is equal to 8z. So x squared plus y squared equals 8z. And that is a paraboloid. So this is a parametric representation of a paraboloid. This one is a little nicer. But I think after those other examples we won't be intimidated. 3 cosine v cosine u I hat plus 3 cosine v sine u j hat plus 5 sine v k hat. So which pair of coordinates are we going to relate? X and y. X squared plus y squared. When we square that, what are we going to get? 9 cosine squared v. Now what do we do? Relate this to z. So x squared plus y squared over 9 is cosine squared v. So x squared plus y squared over 9 plus, what do we want to do here? Z squared over 25 So I'm going to say z squared is 25 sine squared v equals 1. What is that? Ellipsoid. Because we could write it as x squared over 9 plus y squared over 9 plus z squared over 25 equals 1. That's an ellipsoid. And what would be the familiar parametric equations that we're writing in kind of an unfamiliar form here? The spherical coordinates. These are spherical. This is the spherical parameterization of an ellipsoid. All right, questions?
So in order to get to the spot where you substituted C in,
Mhm.
you use the Pythagorean identity cosine squared plus sine squared equals 1.
Right.
To get, okay.
Yep. Yep.
Drop the step there.
All right, let me take a look. I want to make sure this is going to match up with.
Square root of u times
Ew.
squared.
That's disgusting.
Oh, is that these that we just did?
No.
No?
We
Sounds
don't
like
have
the
that.
square root of u,
Yeah, we don't have anything that's square root of u.
but it's very similar.
Oh, let me see. I'm trying to figure out what these graphs match, what surfaces these graphs match up with.
Nothing.
1638.
That is a
Bad.
really bad.
Bad thing. But it's
This is
only
bad.
four.
This
It's
is
only 3 hours to do the 4 problems. He's just gonna cry.
Ew, why'd you say?
Did you just say that?
Why? Yeah, why?
Trying to figure out if they are for. These are for the lesson on block day. Okay, I thought they matched up with today. We'll look at those on block day.
It's an egg.
All right, I am going to write an equation now, a parametric equation of a surface, r of u and v, equals u cosine v I hat plus u sine v j hat plus u squared k hat. So that's going to be our parent equation. I'm going to say for this surface 0 less than or equal to u less than or equal to 2, and 0 less than or equal to v less than or equal to 2 pi. First off, what kind of surface is this? Can we see it? X squared plus y squared equals z squared. That's a cone. Z, x squared plus y squared equals z. Sorry. So is it a cone? Paraboloid. Paraboloid. All right. So what I want to determine is, and let me see if this is. Are these on this sheet? No. Okay. What I want to determine is how these other surfaces that I'm going to write differ from this one.
Oh, observations.
S of u and v is u cosine v I hat plus u sine v j hat minus u squared k hat.
That's gonna
So that's going to reflect over the, in 3 dimensions, the xy plane.
its axis of symmetry is on this. Like the thing it's losing.
So that would reflect over the xy plane. And this, the fact that we have 0 less than u less than or equal to 2 and 0 less than or equal to v less than or equal to 2 pi, that gives us just the upper portion of the cone. All right, the second one, S of u and v is u cosine v I hat plus u squared j hat plus u sine v k hat.
It's on a different axis.
It's on a different axis. What's going to be its new axis? The
Why?
y-axis. It's going to be along the y-axis.
Connor.
The third one, S. Oh, these should be vectors. I would have lost a point on my test for that.
Mr. Beamer.
S of u and v is u cosine v I hat Make sure I write the right one, so I'm not writing the same one down. Plus u sine v j hat plus u squared k hat. 0 less than or equal to u less than or equal to 3. 0 less than or equal to v less than or equal to 2 pi.
So that's gonna make it taller.
Yeah, that'll make it taller. Because this one just goes from 0 to 2. This one goes from 0 to 3. Last one of these, for S of u and v, my little vector. For u, cosine v I hat plus 4u sine v j hat plus u squared k hat.
That's gonna stretch it out.
That does what?
It's going to, instead of just making the whole thing taller, it's gonna like pull it so it's narrower, or it might be wider. Yeah, it's gonna be wider and
Wider?
yeah.
Because if I make my relationship again, I would get x squared plus y squared equals 16
Okay, yeah.
Z.
It would be like stretched out.
So it'd make it wider.
Yeah.
The circles that would the level the level curves would be larger diameter. So this would be wider.
Hang on, does this mean they would like increase in their radius faster?
Yeah.
So
Mhm.
the delta between the two level curves would be
Right.
greater.
Hmm. So
Okay. So it's not
as
like
opposed
it
to
just
that.
starts bigger?
No,
It's-
because it still starts at the origin. Right. Last one. Last example. This time we're going to go from rectangular coordinates to a parametric representation of the surface.
Whoa.
So we want to find a vector valued function This is another type of problem that you might see on the quiz, this type of problem. So we want a vector valued function whose graph is the surface x plus y plus z equals 6. A plane. So we want to parameterize this as a vector valued function, as a parametric surface. So we can write an explicit representation of this surface, right? We can say z equals 6 minus x minus y. So then we can use x and y as our parameters. So r of x and y is just going to be xi hat plus yj hat plus 6 minus x minus y k hat. And if you wanted to, you could let x equal u and y equal v and write it as r of u and v. It's the same thing. This is fine. How about four x squared plus y squared equals 16. We don't have z, so z can be anything, right? Or v. So what do we want to do with this, though? Let's write this. Let's write it in standard form. I'm going to divide by 16. X squared over x squared over 4 plus y squared over 16 equals 1. There's our, so we get an elliptical cylinder. So what are we going to let x equal 2 cosine u, y equals 4 sine u, and z equals v. And then we get this relationship between x squared and y squared that we want. Z can be anything. So our vector valued function, u and v, would be 2 cosine u I hat plus 4 sine u j hat plus v k hat. And that would be a nice parameterization, vector valued function of that surface. Yes?
Where did you come up with the x equals 2 cosine u and y equals 4 sine u?
Because I want x squared over 4 plus y squared over 16 to equal 1. So if I square this, we get 4 cosine squared divided by 4. Okay? All right. Now the reason that we want to parameterize these surfaces is what we're going to do is start talking about surface integrals. And we want to talk about a little element of area on this surface. And we're going to use this parametric representation of the surface to come up with a representation for a little element of area. What do you think that little element of area is going to involve? If I have two vectors, I can take a partial, take the derivative of this with respect to u. That's going to give me a vector pointing in one direction that's tangent to that surface. Take the derivative of this with respect to v. That's going to give me a vector in another direction that's tangent to that surface at that point. Take the cross product. Magnitude of the cross product is going to be approximately the area of that little piece of surface. And we're going to integrate that over the surface.
Oh, good.
So is it kind of a crazy idea of we're integrating a cross product over a surface? So would you, when you were back in pre-calc, would you ever have imagined that that's what you're going to do with a cross product?
I mean,
Yeah, that's you thought about that when we were doing cross products. Like we're going to integrate. We're going to do surface integrals. All right.
I thought you'd never use cross products again.
Right, cross products were just something that they tortured us with in pre-calc. What is today? Tuesday?
Yeah,
I know how to do that.
I just thought like, okay, yeah, I'm gonna do this one test and I'll try to do it actually do it again, and then now everything's a vector.
All right, there you go.
It's all vectors.
Determinant's Dylan.